All right, ladies and gentlemen, if the stream is working, I believe you guys can see my slides here. All right. My name is Tyler Steggy. I'm the former mechanical co-lead for the Purdue IEEE ROV team. For those of you who are hanging out in the Discord this evening, the last session was run by Joe Navarro, the current mechanical lead for ROV, and I'm sort of helping out, filling in this evening. So, as far as how this will goes, we have Angelo. I should remember your last name, Angelo. the head of the Purdue IEEE Learning Committee is hanging out in the Discord in the general voice channel. If you guys have any questions there, feel free to ask him. In the Discord and also in the YouTube description, we have a link to the tiny URL with the slide deck for this evening, and also a zip file with the parts that you guys will need for the exercises later on. That might be a little tricky. If any of you guys are using Purdue Software Remote, in order to get those files in a place that'll be accessible via Software Remote, you'll need to have your Purdue network drive mapped to your personal computer, and you should be able to get the files over if you have that set up. And then, of course, if you have SOLIDWORKS on your personal computer, then that'll simplify things. All right, with that out of the way, we'll get started. All right. Yes, so this is session 2 of 3 for Introduction to SOLIDWORKS. This session is on assemblies. Next week will be the final session, in person on Wednesday, and virtual again here on Thursday, same time. Quick notes before we get started. We may not have mentioned this in the first session, but setting up keyboard shortcuts are definitely worthwhile in SOLIDWORKS. They can really help speed up your workflow. I have a lot of them set up, and I'm going to do my best to not use them today, so you can make it more clear which tools I'm using. But I'd recommend something like the Smart Mate tool, which we'll be using quite a lot. I'd recommend mapping that to something like M or a similar key, whatever feels natural. Yeah. All right. So assemblies. Why do we care? As a general rule, it is very uncommon that anything we'll be using CAD for is the design of a single part. That's very rare. Most of the times we're designing, assemblies of parts that have to interface with one another. Sometimes assemblies that have to interface with existing parts. In fact, frequently interface with existing parts. And so we need to know not only how to design our parts, but how to organize them effectively into these quote-unquote assembly files. So sort of the high-level overview of product lifecycle management. We're still here in the design phase. Next session, we'll be talking a little bit about drawings and documentations, and then come the spring, we'll have a separate training session for CAM, that's computer-aided manufacturing. We'll be doing that with a tool called Fusion 360. So, CAD is largely, there are a lot of tree structures embedded in how CAD is set up. So within individual parts, you'll have the actual part file. Within that, you have your datums, basically your coordinate system. And then when you go to create a sketch on any given plane to create your 2D geometry, that references those datums. And then say you have a sketch of a circle, you extrude that for a cylinder. That extrusion is then referencing the sketch. And you end up with this sort of network, this tree structure of dependencies. The same is true on the assembly level. So you'll have your master assembly, and then within that you can insert individual parts and also other assemblies, which act then as sub-assemblies with their own child parts. And you can have duplicate parts, you can have duplicate assemblies, all sorts of things. So the actual assembly files in SOLIDWORKS, the file extension is .sldasm, similar to the part files .sldprt, solid assembly and solid part. So there's not actually that much information that is stored in the assembly file. Even if you've got an assembly with like 1,000 parts, the assembly file itself is not storing the geometry. What it's storing is its coordinate system, so its reference geometry, its datum, planes, and what have you, and then links to your part files. And that's part of why file management is so important with CAD, is because you want to take great care not to break those links. And then the final bit of information stored in assemblies are the mates, the constraints that relate the parts to one another. So in industry, any company you guys go to work for will have their own system for developing internal part numbers. And there'll be a convention you'll have to follow. And odds are that when you're actually working with assemblies, the only name you'll see for each part is the part number. And that can get confusing. For our purposes, on the ROV team and any personal projects you're working on, it definitely simplifies things just to stick with names and then follow a pretty consistent nomenclature. We'll go over a few tricks or a few examples of nomenclatures in the exercises. All right. So now constraints. So you may recall this graphic from session 1 when we were talking about the process of applying constraints and dimensions to sketch geometry in 2 dimensions. For example, if you create a line here, you just draw it out in space. What you've effectively done are created 4 independent variables that can vary with no set values or bounds. You have the x and y positions of both of the endpoints of this line here. And as you apply constraints, for example, a horizontal constraint here that sets the y-coordinate of point 1 equal to the y-coordinate of point 2, or as you apply dimensions, here applying, say, the length of this line is 18 millimeters, thus x2 is x1 plus 18 millimeters. As you're doing that, you're applying equations that constrain these values until you ultimately end up with 0 degrees of freedom. And in SOLIDWORKS, in sketches, unconstrained geometry is blue, and what you want is fully constrained geometry, and that turns black. Now we have a similar thing in 3 dimensions. So a rigid body in 3D space has a total of 6 degrees of freedom, 6 sort of coordinates that can vary independently. You have your translational degrees of freedom, your x, y, and z position, and then rotational degrees of freedom. In this graphic here, those are indicated by u, v, and w. Borrowing terminology from aerospace, we may call those sometimes roll, pitch, and yaw. And basically what we're doing is we apply constraints that slowly, just as we were doing with sketches, we're applying constraints that slowly constrain those degrees of freedom. So in this graphic here, you have some part, and let's say we want to make the bottom face of that part coincident with this plane, the XY plane. When you do that, you actually lock out 3 degrees of freedom. It can no longer translate vertically in the z-axis, and it can no longer rotate about the x and y axes, so those u and v rotational degrees of freedom. It can no longer do those. It can still rotate about the z-axis, and it can still move in the xy plane. So to further constrain that, so we want to make the rear face of this part coincident with that, the yz plane there. And when we do that, we lock out translation in the x and rotation about the z-axis, that w there. So now it can only slide left and right. And so with one more constraint, we say make the left face of this part coincident with the xz plane. That locks out our final degree of freedom, and this part is now fully constrained with respect to the xyz coordinate system. So I'm going to pop over to SOLIDWORKS real quick and demonstrate that. All right, so I'm going to open up just a demo part here. All right. So let's say we've already designed this part, and now we want to insert it into a new assembly. So what we can do is go up here to File, New, select Assembly. So this creates a new .sld ASM part file. And when we first create a new assembly, it'll automatically ask us to insert our first part. And you can see here any open documents we have, these shows up here. If we want to find something else, you can hit Browse and navigate to whatever file you want through Windows Explorer. So I got this demo part here, and you can sort of see it's sort of asking me to place this somewhere in XYZ in 3-dimensional space. We don't really have any frame of reference for now. So I'm just gonna place it right there. And so you may notice, so I'm going to go ahead and turn on the visibility of the datum planes of this assembly, and just for reference for visibility things. So each individual plane here has its own visibility control. You can see we can hide it and show it in the graphic there changes. And then within each part or assembly file, there's a separate override. If you go up to here to this sort of toolbar underneath the ribbons and this little eye graphic there and hit that drop down menu and turn on visibility for planes, that'll let us see what's going on here. So if you orbit around, you may notice this part was just, when we clicked inserting this part, we just placed it sort of at this arbitrary location in 3D space. So, and what we want to do is make sure that the coordinate system of this part is in a known location with respect to the coordinate system of the assembly. And why that is, we'll get into a little bit when we get into sort of the exercises in this session. There are a number of reasons why you want that. So when you insert your first part, SOLIDWORKS by default just gives it sort of a fixed constraint. So if you see here in the feature tree, this is the name of this part, S2_demo1. And you can see this sort of little series of characters, open parentheses, lowercase f, close parentheses. That indicates that this part is fixed in 3D space. And we want to constrain it ourselves. So I'm going to right click on this and go down to float. So that essentially gets rid of SOLIDWORKS' default fixed constraint. You now see we have open parentheses dash close parentheses. That is SOLIDWORKS' way of letting you know that this part is not fully constrained. So to constrain it, I'm going to hit this drop down menu. It gives us access to the features within this part. I'm going to go ahead, just for clarity, turn on the visibility. Actually, no, never mind. I'm not going to do that. What I'm going to do here is I'm going to go up to the mate tool up here. SOLIDWORKS calls it mate. We'll use the term mate and constraint interchangeably. You know, packages like Autodesk Inventor just call them constraints. So I'm going to go up here to mate tool. And we now have this dialog box. Excuse me. So I'm going to select to be consistent with our graphic actually, I'm going to select the bottom face of this part. And now I'm going to select, what is this, the top plane of our assembly. And when I do that, you'll see the part sort of snapped down. So we've locked out 3 degrees of freedom here. It can still move in the XY plane here. And if we go up to move component, the move component tool here, drop down and go to rotate component, and we're in sort of a free drag mode, you can see it can also rotate about, in this case, the Y-axis. So what we're going to do is we're going to apply our second constraint. I'm going to go up to the mate tool again, click the rear face of this part, and select the front plane of our assembly. And when I did that, you see it snapped there. I'm going to hit this checkbox here. And now, at this point, it can still move left and right. It can still move in the X direction here. So to lock out our final degree of freedom, I'm going to go back to the mate tool, click this left face here, and click the right plane there. So when I do that, this part is now fully constrained, and you'll notice that series of characters, the parentheses with the dash, are now gone. So that indicates that this part is fully constrained within this assembly. And I'm going to go ahead and save this assembly. I'm actually going to overwrite. This is the same assembly from the in-person training. I'm just going to overwrite that. All right. So that is fully constraining a part by constraining faces to planes, essentially planes to planes. However, that is not our only option for constraining. So I'm going to go ahead and open up a second part here. All right. Now, frequently we have unlike sketches, where sketches we generally want the geometry to be fully constrained. In assemblies, we don't always want that. In assemblies, if we're designing a motor, for example, and we have the rotor, the spinning part, we want that in our assembly to be able to spin. So I'm going to go ahead and create another new assembly here. And I'm going to insert this rotor here. This is a rotor from a 3D printed DC electric motor. I'll place that there. Again, SOLIDWORKS added this fixed constraint by default. To get rid of that, I'm going to right click and hit float. Again, I'm going to make these planes visible. again, undo the override there so that's all visible. And I'm going to make this part here has an axis in it. I'm going to show that as well. There we go. All right. So when we're constraining parts, we're not limited to just planes to faces or faces to planes. We can also constrain axes. So here, in order to give us an axis to constrain to, I'm going to go ahead and click the assembly's right plane and the assembly's top plane. I'm going to use that to define an axis. I'm going to go up here to Reference Geometry, Axis. You can see here this is basically using the intersection of two planes to define a new datum axis. So I'm going to hit OK there. So we now have an axis in our assembly that actually is coincident with the z-axis. Now, in order to constrain this part, I can go to the Mate tool. I can select the axis within the part and then the axis that we just defined within our assembly. And when we do that, so that has locked out all but 2 degrees of freedom. Interestingly, so this can still rotate about this axis, and it can still slide along that axis. Now, if this is a part that's only rotating, it doesn't in reality doesn't have a degree of freedom sort of axially. So we're going to go ahead and constrain sort of the rear face of that part to the front plane of our assembly. And you'll notice here that that series of characters, the parentheses dash parentheses, is still there, meaning this part is not fully constrained. However, in this case, since it's a part that spins, we don't necessarily want it to be fully constrained. So here we're using the constraints within SOLIDWORKS to sort of replicate the constraints in the actual assembly or an actual part. All right, so moving back here. So, and just as a reminder, if you guys didn't see the tiny URL in the Discord and also in the YouTube description, that link will take you to the parts we're going to be using for these exercises. So what I'm going to do is I'm going to go ahead and I'm going to open up these parts here. So I provided for you 3 parts: this base, this fitting, and these screws. So I'm going to go ahead and open these up in SOLIDWORKS. And by the way, so SOLIDWORKS, it only ever has one instance of the application, so that you can't have like 2 separate SOLIDWORKS windows, but you can have multiple things open at once. In order to switch between those, you can go up here to Window. And by the way, this is, I believe this is unpinned by default, so you may have to hit this sort of, like if you hover over that sort of arrow there, these options will show up. I'm going to pin that just because I like to have it like that. So I'm going to hit Window here, and you can see, so these are all the parts and assemblies that are currently open. I'm going to go ahead and close out some of those demo parts I was just showing you guys. All right, so we're going to go ahead and create a new assembly. And before I do anything, I'm actually going to go ahead and save this. Go ahead, Control S, as navigate to the right folder here. I'm going to save this as a.exercise1. This is preceding assemblies with a dot in the file name is a good way to make sure that they always sort of show up at the top of the list of files within a given folder that can help make things clear when you're navigating your file management system. All right. So now, to insert a part, I'm going to Insert Components. I'm going to insert Exercise 1 Base here. So again, like before, SOLIDWORKS by default just fixed that at whatever sort of arbitrary location in 3D space you clicked on. So I'm going to right-click on that, hit Float again, so that's to unconstrain it, so it can now move. And now we're going to constrain it the way we want to constrain it, as opposed to how SOLIDWORKS assumed we wanted to constrain it. So we're going to access the data and features within this part. I'm going to hit the drop down there on the part within the feature tree. Now what I'm going to do is I'm going to go up to the Mate tool. And this is a quirk of SOLIDWORKS. A lot of the tools that require dialog boxes for you to input values and such, it sort of takes the place of the feature tree. So if you see there's sort of, in order to click on the things you would generally click on in the feature tree, there's this extra drop down you can click up here. and that'll give you access to those sorts of things. So I'm going to select the front plane of the part. I'm going to go ahead and constrain that to the front plane of our assembly. Hit the checkbox. I'm constraining the top plane to the top plane, checkbox, and the right plane to the right plane, checkbox. So when I just did that, so now the sort of the coordinate system of the part is now coincident with the coordinate system of the assembly. And part of why we generally want to do that and not just leave this part at whatever arbitrary location it was when we started the assembly is because now if I want to go one level up, if someone else is working on an assembly and they're going to insert my assembly into theirs, then they'll want, in order just for convenient access or convenient manipulation, it's nice if the parts and the coordinate system of the assembly have a defined relationship. In this case, they're just coincident. All right. So now we got that out of the way. I'm going to go ahead and insert our next component, exercise 1 fitting here. I'm going to place that right there. All right. So if you'll notice by our graphic, so this part here is asymmetric. It's got this extra shoulder here on this side of the flange. And if you look back at the slides, you'll notice, all right, we want that on the outside. And it's also, so this sort of the central axis of this fitting is going to be coincident with the axis of this hole. So in order to do that, I'm going to go ahead and turn off the visibility of these planes just for clarity. And just to clarify, I'm clicking the front plane there, hitting Shift, hitting right plane, and that's selecting everything in between. I'm going to go ahead and hide that. So now, again, this part is fully constrained. This part is not constrained. So go to Mate. I'm going to select the cylindrical face there, and then select the cylindrical face here. And so what that does by default, the Smart Mate tool assumes that we want these concentric. So what that's actually doing is taking the central axis of both of those faces and making those axes coincident. But in doing so, it has assumed that we wanted those axes coincident with this part in this orientation. And that's the opposite of what we want based on this figure here. So one thing we can do, and you can do this while you're defining the mate, but if you mess up and hit the checkbox before you had everything the way you wanted to, in order to edit that mate, you can actually click on that fitting, hit the drop down on this folder here, mates in a.exercise1. So this is all the mates applied to this instance of this part within this assembly. So that right there, concentric 1, that is the constraint we just created. So I'm going to right click on that and hit flip mate alignment. Now, so that actually goes to the second of the 2 available solutions that SOLIDWORKS can create. All right. So now we got that in the orientation we want. Now we just want to finish constraining it. So I'm going to go back up to the mate tool. I'm going to select the rear face of this flange. I'm going to select the front face of this base part there, and then that'll snap. And so now, the only degree of freedom left to constrain is rotational. So I'm going to select mate. I'm going to select, and you want to be careful with this. I'm going to select the cylindrical face and not the actual circular edge here. And I'm going to do the same thing with this hole. I'm going to select the cylindrical face. SOLIDWORKS is relatively smart with this. So I'm gonna, for the sake of argument, I'm going to go ahead and track down that constraint I just created. I'm going to go ahead and actually delete that just to show you something else here. I'm going to go back up to mate. If I select this edge and select that edge, that'll still technically work. In other packages, they might treat this a little different. I remember, for example, Autodesk Inventor, when you select circular edges like that, it's actually just constraining the points, the centers of these circles. So it sort of ends up acting like a universal ball and socket joint. SOLIDWORKS is a little smarter. It's assuming that what you really mean is the axis that is perpendicular to this circular edge and coincident with its center. So this will effectively do the same thing. All right. Now I got that out of the way. All right. Now our fitting is now fully constrained. You click on it and try to drag it. Oh, it doesn't go anywhere. That's what we want. And I'm going to go ahead and hit Control S just to save our progress. Now, one of the things you'll frequently find when designing assemblies is that you tend to use a lot of, at least mechanical systems, you tend to use a lot of fasteners, lots of screws and nuts and bolts and what have you that are standard parts that existed, that already exist, and it's efficient. We could, if we wanted to, take a bolt and a pair of calipers and take some measurements and model it ourselves, but there's no real reason to. We generally want to include fasteners, just to make sure that there's room for the head within the parts we've designed. Make sure there's tool access so we can actually tighten it. So we won't include it, but we want to do so with the least amount of effort on our part. So a lot of standard parts we can find models of online. So I'm going to go ahead just into a browser, drag this over, and McMaster-Carr is a great source of 3D models for standard parts. So I'm going to go over, it's McMaster.com. In this case, I believe we're looking for M10 socket head cap screws. Now, I actually already provided these files, so you guys don't have to do this. If you're following along, you don't have to worry about this. But I believe these are M10 by 35 millimeters. So I'm going to go to screws and bolts here. System of measurement metric. M10 means it is a metric fastener, metric screw with a 10 millimeter nominal diameter. So I'm going to go to metric. Socket head screws right here. Thread size, I'm going to scroll down to M10. And length, I believe these are 35 millimeters long, so I'm going to select 35 millimeters. Now, there are a lot of options here. Most of these are going to be pretty much the same geometrically. So I'm just going to simplify things. I'm going to go ahead and select a specific material that I know that we use a lot on RV, for example, which is 18/8 stainless steel. All right, so that gets us to. So that sort of applied all the selection filters, and that gets us to a part here. And in McMaster, if you hit the drop down and then hit product details, that'll take us to a page for M10 by 1.5 millimeter thread. That's if you're not familiar with thread standards, that's a useful thing to get familiarized with, but that's not within the scope of our training here. Scroll down, you can see a part drawing, and over here, these are the 3D models it has available. So McMaster is actually unique where it has SOLIDWORKS specific files. All the rest of these are what are called dumb file types. So like a 3D step here, that is a step.stp or .step file extension. That is a very commonly used sort of quote unquote dumb file type used for transferring models between different packages, different softwares that have their own, they'll have their own unique proprietary file type. But step is a good sort of, what would you call it? Intermediary file type. It doesn't store all the information. It basically just stores the final geometry. So it's harder to edit than if you're dealing with a part within the native file type. That's a material though. So I'm going to go ahead and select the 3D SOLIDWORKS option. I'm going to go ahead and save that. And you'll see here we can open that up in SOLIDWORKS. So, and then I'm going to go ahead and make some of these sketches invisible, because when we have this in a larger assembly, we don't need to see all that. Now, one of the things you might want to do with fasteners like this is, this sort of helix here, threads they're a complicated geometry. There's a lot of polygons that go into defining that and viewing it. So to make it easier on SOLIDWORKS, if we've got an assembly with a lot of fasteners and a lot of parts, just to make SOLIDWORKS run a little bit faster, sometimes we might want to go ahead and find that the feature that creates those threads. In this case, cut-sweep1. We're going to go ahead and suppress that. Suppressing, by the way, is sort of a way to turn off a feature without fully deleting it. If we deleted it, then it'll be gone from this feature tree. But if we suppress it, it'll turn it off on the model. But if we wanted to, we could go and unsuppress it, and we'd get that geometry back. Anyhow, this is a lot simpler and easier for SOLIDWORKS to handle, which is why the file that I actually provided to you guys did basically the same thing. So I'm going to go back to our assembly here, go up to Insert Components, select that screw there, and I'm going to place that. Now to get this in the right location, I'm going to go ahead and hit mate. I'm going to select that there, select that there. And you can see again here, so it made those two axes coincident, but there are two ways that those axes can be coincident. The bolt can be in this orientation or it can be flipped 180 degrees, and both of those are equally valid. And SOLIDWORKS just chose the one of those two solutions that was closest to how the parts were already oriented. So while we're still defining this, we actually have the option here of hitting this button here, flip mate alignment, and that'll flip the bolt around. So I'm good. Hit the checkbox. Now I'm going to go ahead and drag this over there. While it's still not fully constrained, you can drag it around, and that's convenient. And now we're going to constrain sort of the bottom face of the head there to the outer face of this flange. And there we go. Now you will notice that we still have those series of characters there in the part that indicates that this is not fully constrained. That's because we didn't actually constrain it rotationally. For a screw like this, it doesn't really matter. If we want to just make things a bit easier on SOLIDWORKS, we can track down that constraint there, the concentric constraint, and right-click and just hit lock rotation. That'll just freeze out that last degree of freedom. That just makes it a little bit easier on SOLIDWORKS to solve for all of your constraints in a big assembly. But it doesn't matter too much. All right. Now, in order to get the other three fasteners in here, we could just replicate exactly what we did just there. We can go, insert components, select that, place it, and then apply those constraints just in the same way. But, we're engineers. We're lazy. So actually, instead of doing that, there's a couple other ways to do this. So I believe if we hit the drop down on the fitting, there is an axis in there, and I'm going to make sure that our axis visibility is turned on. So again, that eye looking tool up here, hit view axes. All right. So what we're going to do, well, there are a couple different ways to do this, but I'm going to show you a couple. One option here is if you go up here to linear component pattern. That's just this is one option. Hit the drop down menu. This will give you all of your component pattern options. I'm going to select circular component pattern. Since we already had the screw selected, it auto-populated this here. So components to pattern, selected the screw. If you go up here, it gives you the option here to select the axis you're patterning about. So I'm going to go ahead and select that axis there. And there are a couple different options here. By default, it's going to make everything equally spaced within 360 degrees, and then it'll give you the option to change the number of instances you want. In this case, we want to change that to 4. Again, not what we want here, but if we wanted to do something different, we could uncheck equal spacing there, and then we could pattern things. So 4 instances, 30 degrees offset from one another. That is also an option. But again, here, so we want equal spacing. Just going to leave that checked. And if you hit the checkbox here, we now have 4 copies of our fasteners. And we have everything modeled as we wanted to model. There is actually another option, with CAD, it is very, very frequent that there'll be a lot of different ways to accomplish any given goal, and they'll all have their advantages and disadvantages. In this case, say we wanted to increase the number of fasteners here to 6. If we go to the base part here, and we change the way this is built is it's just got this hole here, and then it patterns it. So if we want to edit that and say make it 6 fasteners, and we go back to our assembly, we now end up in this awkward situation where we have 6 holes but only 4 bolts. I'm going to go ahead and undo that. There is another option for a component pattern that would update if we change the number of holes, and that is, I'm going to go ahead and suppress that circular pattern there. And that is, if we go up here to component patterns, the pattern-driven component pattern, which is a bit funny to say. So we need to select our component pattern. You can either select the actual fastener like there, or you can go to this drop-down menu and select it from the list there. And now this will let us pattern the screw here based on some existing feature or pattern within one of the parts. So in this case, I'm actually going to select that circular pattern within the base part that I just edited to 6 and then back again. Go ahead and select that. And you can see that'll fill in the other 3 screws. And now, if we were to go to the base, this will be a little bit funky because I didn't actually constrain the screws based on the base. I constrained it based on the flange, which won't update as we do this. But if you wanted to update that to 6 and then go back to the assembly, that'll update the pattern of screws to 6. And again, we don't have the fitting here. That isn't tied, or that isn't referencing anything, so we'd have to update that separately. But our screws will auto-update. So that is, again, all the different methods have advantages and disadvantages. If we were using just a circular pattern, we'd have to separately update the number from 4 to 6 within the assembly here. And just one last time, I'm going to switch that back. All right. So, cool. I think that covers most everything I wanted to show you guys here. Actually, just belay that. There's one more thing I want to show you guys while we're here, and that is replacing components. So I mentioned earlier that the actual information that is stored within this file, within this .sldasm, the actual assembly file, is just, it's got the datum, it stores this datum geometry here, it stores links to these parts, and it stores all of the mates that relate them. So if we were to change the name of one of these parts in Windows Explorer here, if we were to change this name, rename it to something else, that'll break the link. That does raise a question. It's like, all right, what if we want to, say we want to make a new version of this fitting? But we want to make it like a new version in parallel. Like we're undecided if this change that we're making, if we want to stick with it. So I'm going to go ahead and copy that, paste it. Let's say we want a new version of this fitting, and we'll call it, the same name, but add an underscore B at the end there. Well, let's open that up. And let's say a machinist took a look at this part and decided this sort of decorative flare on this flange is unnecessary, and to make it simpler to manufacture, we just want to make this circular again. There are slightly smarter ways, or depending on how you constructed the model, there are different ways you'll need to do this. In this case, just sort of a quick and dirty option. I'm going to edit the sketch that sort of drives this extrude feature. And you can see here we have some construction geometry and then the actual geometry along the outside that defines that's being used by the extrude feature. I'm just going to go ahead and hit the circle tool. And I'm just going to make a circle that is tangent with that. And again, this is just a quick and dirty edit. So instead of actually deleting this geometry, I'm just going to make it quote unquote construction geometry. So it's no longer contributing to the closed loop that we need to extrude. And to simplify that, I'm just going to go ahead and select and hit Control and select all these lines and then make those for construction. All right, that was just a quick and dirty way to change that sort of fancy shape to a simpler geometry. And that actually broke a few things, but we're not going to worry about that right now. If we go back to our assembly, so if we wanted to put in the new version of our fitting, we could just delete this fitting here, but that'll also delete all of the constraints we already set up with this fitting. So instead, I'm going to right-click on this, and you'll have to follow this drop-down menu, this arrow down, and you'll see this option here, Replace Components. So I'm going to hit Replace Components there, and this will let you replace these components with this one. And I believe, yeah, Exercise 1, Fitting B. That's just the files you have open. I'm going to hit the checkbox there. All right. It doesn't like that. That's because we need to tell SOLIDWORKS what, there's a constraint that's referencing this face, and we need to tell SOLIDWORKS, okay, what is the equivalent face on this new part we've just told it to insert. And SOLIDWORKS has this nice handy tool to do that, to make things simple. I'm going to hit the isolate button here. That'll just make it so we're only looking at the fitting. So isolate selected entity. So that'll just hide the rest of the assembly. All right, now, so I need to tell it what face on this part is equivalent to that face on the part we are replacing. So I'm going to select this rear face here. Cool. I'm going to hit the next arrow. All right, now it's asking what is the equivalent edge to that edge on the part we're replacing. So I'm going to select that edge there. Cool. And then it already knows which one's that. This is the last one in question. It's asking, you know, what face on this new part is equivalent to that face on the old part. I'm going to select that front face. You can see all of the references here are green checkboxes. I'm going to hit OK. And cool. So that we just subbed in a new part and managed not to break any of the constraints. Awesome. And with that, I believe that is all I wanted to cover with this exercise. Let us know in the Discord channel. I'm in there, but I'm muted and deafened. But let Angela know if you guys have any, if you guys have been following along, if you guys have any issues or questions you want to ask him about, feel free to tag Angelo there. I'm going to go ahead and basically close out all of these, everything we've had open so far, just to clear out our workspace a little bit. All right. So that is exercise 1 down. So now we are going to move on to exercise 2 here. Again, you guys should have these files. I'm going to navigate to my exercise 2 folder here. And then there should be a total of 5 distinct parts that we provided to you guys. So I'm going to go ahead and open each of those up. We got this main enclosure here. We have a rubber gasket. We have a sort of a polycarbonate translucent lid. A button head cap screw. And an underwater waterproof electrical connector. So those are the 5 discrete, unique parts in here. So I'm going to go ahead and create a new assembly. So I'm going to start out sort of our most natural, looking at this assembly, sort of the most natural part to quote unquote call our base part is the actual enclosure, the actual box here. So I'm going to go ahead and select that first. Go ahead and place that. Once again, I'm going to make our datum planes here visible. You can see this is fixed, so I'm going to right click and hit float. So this is now unconstrained, and we can constrain it the way we want to. So I'm going to go ahead and select, previously to do all these mates, I've been telling you to go up to the mate tool and then select your faces. There is a slightly quicker way. If you're, you can actually just select the 2 planes you want to constrain, and if you select one and then hold the control button and select another, and then you'll get this. You'll get this sort of quick mate sort of dialog box, or not dialog box, whatever you call that, will show up there. And I'm going to go ahead and hit coincident. I'm going to do the same thing with the right plane, and then I'm going to do the same thing with that top plane there. So I'm just constraining the front plane of the part to the front plane of the assembly, and the same thing with the other ones. There we go. So now we have placed our sort of base part here within the assembly. All right, I'm going to go ahead and hit save. Navigate to our exercise 2 folder here, and I'm just going to use the same nomenclature we used on the first one, a.exercise2. And so you'll notice if you actually view within the folder here, because we added that A dot, that'll just jump to the top. It helps keep things a little bit more organized. But there are plenty of different ways to do that, and plenty of people have their own preferences. I know, I know that I know there are some disagreements even within some of us on RV as to what's the best nomenclature system. Anyhow, moving on. So we've got the enclosure in there, so we're going to go ahead and insert the rest of our parts. I'm going to go to Insert Components, and go to Gasket next. Now, we have a couple different ways we can constrain this gasket to this lid. What I'm going to start out by doing is I'm going to constrain the bottom face of this gasket to the top face of the enclosure. Hit the checkbox. So now we need to constrain it within that plane. So one option we could have is we could constrain that via the holes. So if I select there and there, that'll constrain the part, and you can see it's now just got 1 degree of freedom left, and then we can finish that off by constraining there to there. You can see all of our holes line up here. Alternatively, if you don't want to constrain via the holes here, you could actually constrain, say, the front plane of the gasket. You could constrain that to the front plane of the enclosure. And there are various advantages and disadvantages. If you constrain based on the holes, and say you're editing one of the parts and one of the holes moves on you and you didn't plan on it, when you go back to your assembly, if SOLIDWORKS can't resolve it based on the hole locations, it'll give you a warning. It'll yell at you, and that's a good way to catch potential errors. On the other hand, if you know you're going to be making changes to this hole pattern, say this is currently, what is this, 10 holes? Let's say I know I might change it to 8, and I don't want to worry about breaking links in the assembly. Maybe I'll constrain it based on the planes, and that'll bypass that issue. So again, advantages and disadvantages, and it depends what your priorities are. For now, to keep things simple, we're just going to constrain off of the holes. So I'm going to go ahead and do the same thing with the lid. So I'm going to insert the lid here. If I believe, yeah. Let's go to Mate. And so this is going to be, transparent parts can be a little funky, where if you try and, you can see here, like I'm just hovering over this part, and instead of selecting it, it assumes you're trying to select the thing behind this part because this part is transparent. If we wanted to, we could right click on the lid and turn off the transparency, and that makes it just a solid white. I'm just going to leave it like that for now, though. All right. So now mate selection. So I'm going to select that interior, the face of that hole, and I'm going to constrain that to the face of the lid there. And you can see it actually, this happens quite a lot. Like after you apply your first or second constraint and you don't quite have your part in the location you want yet, sometimes it'll like jump to a location that is inside another part. You can see those faces are aliasing a little bit. So I'm going to go ahead and try to, and this is another situation where having a transparent part comes back to bite us. I can't actually grab the part. So I'm going to go ahead and turn it back off, the transparency, and we'll just leave it like that for now. All right, I'm going to grab that and just drag it up. All right, I'm going to go back to Mate. Oh, but by the way, a quick note on actually navigating your files, or navigating in 3D space, your view. In order to orbit the view like this, by default with SOLIDWORKS, you click on the middle mouse button, or on the scroll wheel. And then if you want to just pan your view, I believe it is you hold the control button and then click on the scroll wheel, and that'll let you pan your view. All right, moving on. So we're going to go ahead and apply another constraint. Mate there, mate there. And I believe if you guys are using I believe there's actually an error in the files that we gave to you guys. I believe one of the holes in the corner of these parts is actually a little messed up. So if SOLIDWORKS is yelling at you, you try to apply that constraint, and it gives you an error, like it can't resolve it. For now, just go off a base, try to constrain it with a different hole. that is our bad, and you don't have to worry about trying to fix that. Or if you like the challenge, you can dig through the parts and see what's wrong. There's actually one hole that is not constrained within a sketch. Anyhow. All right, so we just have 1 degree of freedom left on this lid to constrain. So what we're going to do there, we're going to navigate around, we're going to select that bottom face, and we're going to constrain that to the top face of the gasket. All right, you can see now the parentheses, dash parentheses is gone from all of these. That means all of these are fully constrained. If you try to click on them and drag them, they won't go anywhere. That's what we want. For a static part or static assembly like this, none of these parts are moving with relation to one another. We want to make sure that in our model they can't move with relation to one another. So now, if we look back at our slides, we have a few more parts to add. We have all the screws here up top. And we also have this panel jack for this underwater connector. I'm going to go ahead and start with that panel jack. Go to Insert Components. Go to, it is that file is called connectors_binder_4pin_male. So I'm going to select that. I'm going to place it. I'm going to go to Mate. I'm going to select this cylindrical face. This is another instance of sort of a dumb file that you can typically find online. So this is from a company called Binder USA. They make underwater waterproof electrical wires and cables and components and such. So I believe this is actually a step file .stp. So again, dumb geometry file that we downloaded from Binder's website. If you're dealing with electrical connectors or hardware, frequently companies these days, in addition to technical drawings, will also provide some basic CAD files. And this is actually a simplified model. So again, remember when we downloaded that screw from McMaster, we manually suppressed the threads to keep the polygon count low. Here, these all 4 of those faces on the actual part are threaded. But to keep things simple, the model just left those as cylindrical faces. So I'm going to go ahead and select that cylindrical face. And this hole would also be threaded, but again, it's just for simplicity, it's cylindrical in the model. Select that. The SmartMate assumed correctly that we want those 2 faces to be concentric. So I'm going to go ahead and hit the checkbox here. And you'll notice here, so this, on the actual part that this model represents, this sort of toroidal surface, that donut shape, is an O-ring. So in actuality, in CAD, all of the solids that we model are rigid. So what means you have some choices when it comes to modeling sort of deformable bodies. In this case, we're just going to go ahead and select deformable bodies like O-rings or gaskets, to clarify. We're just going to go ahead and select that face, and we're going to make it, well, the mate tool will actually assume what we want. I'm going to go ahead and select this face here, and it will assume correctly that we mean that toroidal surface and that sort of flat plane to be tangent to one another. Interestingly, this is another case where there are 2 solutions to what we're asking SOLIDWORKS to do. There are 2 different positions that this could be in that would satisfy that tangent constraint. And the way you can actually switch between them is hit by flipping mate alignment there. You'll see that just sort of moved the part inside the body. And you can see that O-ring is tangent there. But let's just say we want it like this. So I'm going to hit the checkbox. This is another situation where, again, we never actually constrained this rotationally, so that can still rotate. With screws and bolts, it doesn't generally matter. With larger things like this, just to make the model look nicer, I'll tend to constrain them rotationally. And again, so we could, if you hit the drop-down menu and navigate to those 2 mates we just created, I could right-click on this concentric and just lock rotation, but that'll just lock it in whatever position it's currently in. If I want to make it look a little bit more organized, say I've got like 10 of these on the same enclosure, I want to make it look nice. Excuse me. I'm going to go ahead and go up to mate, and I'm going to take this flat, and I'm just going to make that parallel with the top face of our assembly. You can see it automatically assumed I meant parallel. It's because if we tried to make this coincident, it would actually violate, it would over-constrain the system. Like if I hit coincident, I hit checkbox, yep, you can see it's over constraining the system. So I'm actually going to cancel that, and instead, yeah, it did not create the constraint. So I'm going to reselect that face, select the top, and that'll just make them parallel. Did we need to do that? Not strictly, but it'll make things look more organized and nicer. You can see now if we try to drag on it, it's fully constrained. Alrighty. So now the last step is just to insert our screws here. So I'm going to go to Insert Component. I believe that file is called hardware_buttonhead_632 and etc. I'm going to place that. Interesting. It looks like when this is another part that we downloaded from McMaster, and it's got a lot of planes in there that's visible because that's part of what. Well, this is controlling visibility, something you'll tend to do a lot when you're working in assemblies. You know, sometimes you want to be able to see the datum planes within a part in order to constrain them. Sometimes you don't want the clutter. In this case, I could just go up here to the visibility and turn plane visibility off, just to sort of that's sort of an override switch for all planes. So, but now if I wanted to be able to see a plane, I couldn't. So, just sort of as an aside, I'm going to go ahead and right-click on this part. I'm going to go ahead and open it. It warns me that it's an older version. That doesn't matter too much. And I'm just going to hide these planes. I'm going to just make sure none of these sketches are currently visible. They're not. All right. That's just to declutter our view. I'm going to go ahead and hit save. This is actually an older version from an older version of SOLIDWORKS. That doesn't matter too much. I'm going to hit save and call that good. And back out of this and back to our assembly. All right. That's just an aside. If so if you end up with lots of planes, you can go either override the visibility of all planes or go into the part and manually hide those individual planes. Anyhow, moving on. So I want to constrain this. So I'm going to select this cylindrical face here. I'm going to go ahead. I'm just going to go ahead and select that base part there. Again, that cylindrical face, not one of the circular edges. I'm going to go ahead and preemptively just lock the rotation there, because we don't actually care about how the screw is oriented in the model. Hit the checkbox. I'm going to go select the bottom side of this face, select the top of our lid, and call that good. And if you do have this lid still set to transparent, you may accidentally select that gasket. But you can either sort of angle it such that you can select that face without something in the background, or you can right click on that and hit the change transparency. Anyhow. So now a similar situation to our first exercise where we have a lot of screws, but we don't really want to spend the time to manually insert a bunch of copies of the screw and manually constrain it. That's just a pain. We want the low effort option. So here there's no option to just use a circular pattern, and doing a linear pattern here would actually be more trouble than it's worth. So what we're going to do is that same pattern-driven component pattern. So I'm going to go ahead and select the screw, go up here, hit this drop-down menu, go to pattern-driven component pattern. Now I'm going to navigate our drop-down menus here. I'm going to go to the enclosure, so that is the box, the sort of the base part we're working with here. And I'm going to find the feature. There's a hole wizard feature right here that is all of the holes that these screws are actually threading into. So I'm going to select that feature. Oop, I gotta hit driving feature component. Select that feature, and then that'll pattern our screw here such that there'll be one for every hole. Now, I know if you're following along, you might end up with a situation where you'll sort of get this pattern of screws, but it'll be off to a side. I actually got a little lucky here that it does this right. So when you give it this hole feature, it knows the pattern you want, but it doesn't necessarily know where to locate it. So if you end up with a situation where these screws are off to the side, what you want to do is hit select seed position. And SOLIDWORKS is a little buggy. You might have to hit it twice, 3 times. And then you select one of these, the purple dot that'll orient things properly. So you see, yeah. So that's the situation you don't want to be in. So you want to make sure you select the seed position such that it'll orient everything properly. All right. I'm going to hit OK there. And that is our full assembly. Awesome. Quick note for larger assemblies where you've got a lot of different parts and sub-assemblies, just to help keep things organized, sometimes you can add folders within your sort of feature tree here. So if I've got, a bunch of other different types of hardware, fasteners and the like, I might want to organize all those into a single folder. Not a sub-assembly, but just sort of a folder in this feature tree to help organize everything. So you can right-click on something like this and hit Add to New Folder. And I'm going to go ahead and name that Hardware. So now if we've got any extra screws or nuts or what have you, we can just throw those in there, and that'll sort of help keep separate the parts that we designed that we're making from sort of standard parts that you just buy and add. I'm going to do a similar thing here with this. Say this is, sort of the pretense here is that this is sort of an underwater electrical enclosure. So if you have some printed circuit boards in here that you'll model, you want to add that in this connector here to a folder. We'll call that electronics. Again, just to help keep things organized here in this feature tree. That's not required, but useful. Cool. So we can go save all. We are done with that. Cool. So let me know. Again, I'm gonna pause here for a minute or two. There is a bit of a delay between the YouTube stream and Discord. I'm gonna give you guys a minute to ask Angelo any questions if you guys are having trouble, and if need be, you guys can pop out into one of the breakout rooms in Discord and share your screen or what have you. Everyone following along okay? If you are, go ahead and post a message in general, just sort of a thumbs up to make sure that you guys can you guys are hearing the stream properly and that you're following along. All right, we got at least one thumbs up. All right, cool. So we're going to go ahead and move on unless anyone raises any objections. We're going to move on here to this third exercise here. This 4-bar linkage. So this is a bit of an exercise in sub-assemblies. So we've got this assembly here. You can see there are a bunch of different parts, and it's going to be most convenient for us to organize those parts into sub-assemblies that move together. So if I recall correctly, the actual files we provided you guys, there is a number of parts, and then there are two, excuse me, I believe there are two assemblies already in there. So those are sub-assemblies. And I went ahead and named those with a B dot. So again, that'll bring assembly files to the top, and then also indicate that those are sub-assemblies. That way, if we call our sort of master assembly A dot, that'll be at the top and just keep things organized. So I'm going to go ahead and close out of all of these parts just to clear up our workspace. Alrighty. So I'm going to go ahead and start a new assembly. And before I add anything, I'm going to go ahead and just save this. Navigate here to our exercise 3 folder. assemblies don't have to be in the same folder as the parts they reference. But for now, just for simplicity, we're going to keep them there. All right, so consistent nomenclature. I'm going to call the master assembly here A.exercise3. Cool. I'm going to go up to insert components, and we're going to go ahead and insert the two subassemblies that we already provided for you guys, exercise3 underscore base and exercise3 underscore rocker. I'll go ahead and open both of those, and it'll have me place them one at a time. This is the base. I'm just going to place that there. And then this is the rocker. I'm going to go ahead and place that there. So, so this will be a situation where when we're done with this, this won't be fully constrained. It'll have 1 degree of freedom that corresponds to sort of the rocking, sort of the actual motion of the 4-bar linkage as it would be in reality. But this base we're going to want fixed, so I'm going to go ahead and fix that to the coordinate system of the assembly, like the way we've been doing. I'm going to right again that comes in automatically fixed. I'm going to right click, hit float, select front plane, constrain, top plane, coincident, right plane, coincident. And again, I'm going to just go ahead and turn on visibility. I specifically want the, actually, I am going to undo. I'm going to delete 2 of those constraints. To keep things sort of more intuitive, I'm actually going to constrain what is called the front plane in the subassembly. I'm going to constrain that to the right plane. Oop. There we go. Of the assembly. That should keep, we'll get into why in a little bit. And to make sure that's fully constrain the right plane of the subassembly to the front plane of the assembly. All right, cool. So that is now fixed. Our rocker here can still move, but we'll come back to constraining that after we create our other subassembly. So I'm going to go ahead and just save that, Control S, save all, rebuild, and save document. All right, so now we need to create this subassembly. So like I said before, subassemblies and assemblies, they're all the same file type. So I'm just going to create a new assembly. I'm going to hit browse here, and I believe it is exercise 3 coupler. It is these 2 parts that we need. Go ahead and let's select the standoff to start with. I'm going to place that there. Again, I'm going to right click on that, hit float, and then this is important. As we create these subassemblies, we're going to make them all sort of centered about one of the datum planes of their assemblies, and that'll help us constrain all the parts together in the way that we'll want, and that'll become the reason for that should become clear. So I'm going to go ahead and select this what is called the front plane in this part. I'm going to go ahead and constrain that to the right plane of the assembly. And front, top, right, those are all just sort of SOLIDWORKS by default names. What is it? The X, Y, YZ, and XZ planes just gives them names that are a bit easier to navigate. But none of these actually matter too much. Just to fully constrain this, I'm going to go ahead and make those planes visible again for you guys to make it help visualize what's going on here. All right, so I'm going to select just the top plane of this standoff, select that plane there. I'm gonna select the right plane. As you hover over these planes, it'll sort of highlight what it is you're selecting, even if it's not visible. I'm gonna select the front plane there. All right, cool. So this standoff is now fully constrained. So that is sort of our so that's what we'll be basing everything else off on. So I'm gonna go back up to insert, browse, and I believe the part is called link. So I'm going to go ahead and insert that in. You'll see it's not in the actual orientation we want it. By default, no matter. I'm going to select mate, and I'm going to constrain this. Oop, it's not actually that one. Constrain that face, that cylindrical face, to that cylindrical face. I'm going to call that good. Then I'm going to select that interface. of the link to the outer face of the standoff here. Call that good. And then just to lock everything down, because this can still rotate, I'm going to go ahead, hit the drop down menu here, navigate to hover over just, whatever that plane is. In this case, that's the top plane. I'm going to go ahead and constrain that to the top plane of the assembly. Just so everything within this assembly will be fully constrained, and then we'll still have the 1 degree of freedom in the master assembly when we get there. All right, so we actually need 1 more of these standoffs and 1 more of these links. So I'm going to go ahead and select here, as opposed to going to insert and then finding that file again. I'm just going to select that. I'm going to hit Control C and Control V to paste. Very similar mate process. Select that hole, constrain it to that hole. I'm going to select that face, constrain it to that face, and then once again, I have the drop down. I'm going to constrain the top plane to that top plane. Cool. Now I just need one more copy of these standoffs. Again, I'm going to click on it, hit Control C, Control V, mate. I'm going to grab that hole, constrain it to that hole. It was actually was in the, that's the actual final resting place we want it in, but it's not fully constrained yet, so I'm just going to drag it away. So I have line of sight to click on that face, constrain that there. And now this actually, it's very difficult to see because there's no frame of reference, but this part can still rotate. It doesn't really matter what orientation it's in, since it's an axisymmetric part, so I'm just going to navigate through the drop-down menus to that concentric constraint. I'm going to go ahead and right-click and make that lock that rotation. Just make sure everything's fully constrained. That doesn't matter too much. I'm going to go ahead and hide all those planes except for the right plane. So if we did this right, all 4 of these parts are now constrained about, sort of symmetric about the right plane of this assembly. And so the reason we want our parts constrained to the coordinate system, to the datum planes of our assemblies, is so when we insert these assemblies into higher level assemblies, we have convenient access to the geometry we want. And that'll make sense here in a second. So I'm going to go ahead and hit Control Save. Believe that should prompt me. Yes, it should prompt me to give it a name. So to be consistent with the nomenclature we've got here, so A.exercise 3, that's our master assembly, and then so this sub-assembly we've just created is sort of on the same level in the tree structure as these 2 sub-assemblies. So we're going to give that a B. prefix. This is nothing required by SOLIDWORKS by any stretch, but it's just keep things consistent. And then so this is exercise 3 coupler. And we'll give it a version number 1. So you can sort of see here, this is, I believe in computer science, it's referred to big endian. We're starting with so it's the sort of classic conundrum of how do you arrange the year, the day, and the month in the date. And sort of the European convention is day, month, year. That keeps it sort of in increasing order of significance. My preference is actually to go year, month, day. And it's a similar thing. Sort of the typical nomenclature I follow with CAD is when I'm giving it names, it's sort of like the master, the highest level thing. So exercise 3, if this was, you might call this a 4-bar linkage, and then underscore coupler, and then underscore. So it's like master assembly, sub-assembly, and then part. That just keeps things organized the way I like them. You very well may have your own preference, and a lot of people have their own preferences for how to do this. Anyhow, so now I have our sub-assembly. For the sake of time, we're going to skip those screws. It's we already covered how to do that. All right. So we're going to navigate back up to our sort of top level assembly here. We're going to insert the sub-assembly we just created. And bam. Now, So to constrain this, so this base here again, that's sort of our, because that is our base part, we fully constrained that to the datum planes of the assembly. So now what we're going to do is select mate. I'm going to select, that is the sort of the face of the hinge here. I'm selecting that face there. You'll notice we also don't have any shafts or like retaining rings or collars or anything. If this was a real thing you were trying to build, you'd obviously need the hardware there to support the rotation. But for our purposes, we don't care too much. All right, this part can now rotate about the axis, but we have this extra degree of freedom we don't want, and that's the fact that it can move axially. So there are a couple of different ways we could constrain this. We could constrain this face to that face, and if we hit the checkbox there, that does what we want. We now just have the degree of freedom left that we want it to. But I'm going to go ahead, I'm going to back out of the mate tool. For the purposes of viewing here, I'm going to select this face and select normal to. That'll just give us, this view that we want. Ooh. I forgot to make a change. All right. The thing that I intended this to illustrate is not quite illustrated. So I'm actually going to ignore this for a second. I'm going to edit this part. All right. That is what I intended to illustrate. So if this is a real thing that we want to make, we can't make the distance between these faces exactly the same as the distance between those faces, because then there'll be too much friction and it won't turn. So we need some clearance in there somewhere. And my preference is generally to make sure that clearance is evenly distributed across the different sides. And you see here, since we constrained this face to this face, we don't have that. So I'm going to navigate to that constraint we just made. I'm going to click on coupler here, drop down menu on mates, that coincident constraint between those two faces. I'm just going to go ahead and delete that. What I'm going to do instead, and this is something of a preference of mine, is I'm going to constrain the right plane that is of the coupler subassembly. I'm going to select that right plane, and I'm going to constrain that to the right plane of the global assembly, of the master assembly. And I'm going to hit the checkbox. So you'll notice there, if we go back to that normal view, by the way, you can also access that view if you go up here to this toolbar beneath the ribbons, select view orientation. You can either select top, left, front, right views there, or you've got this weird sort of outline box and you can select any one of these faces and that'll give you that view we want. And I've actually connected these. You can see here, right num3 there. That's indicated. I've actually set up a keyboard shortcut on my numpad on my laptop to be able to switch rapidly between these different views. Anyhow, we got this view. All right. So you can see there that the clearance is evenly distributed. And that's just to keep things nice and sort of represent the system in its most nominal state. All right, so we've got the coupler in there. We're going to go ahead and insert another one of these. I'm going to hit that, hit Control C, hit copy. Actually, you know what? I'm going to undo that. This is a good situation, a good example to illustrate another option for inserting multiple of the same thing, and that is copy with mates. So I'm gonna select this. I'm gonna go up to Insert Components, the drop-down menu there. There's an option, Copy with Mates. So it'll prompt you to select a component. Since I already had that selected, it just auto-populated that little box there. I'm gonna hit this next arrow. So there are two constraints that we applied to that subassembly: the hole, making those holes concentric, and then sort of constraining that midplane to the midplane of the assembly. So what's asking here is which one of those do we want to repeat? And we specifically want to repeat that midplane constraint. So I'm going to go ahead and hit repeat there. And then here under concentric, so it's sort of so we've sort of already selected the face of the coupler, but I'm selecting what we want the next one to be constrained to there. Hopefully that made sense. So we told her, repeat that one constraint, and here, keep the same constraint, but replace what in the assembly it's referencing. I'm going to go ahead and hit the checkbox there. And then it'll let us, it sort of assumes you want to add more. If you don't want to add more, I'm going to go ahead and hit cancel. In a situation like this, using copy with mates didn't really save much time, but in other circumstances it may. Just want to make sure you guys are aware that that is an option. All right. So cool. We now have both of our couplers in there. You can see those can both rotate. So now to get sort of the last piece of the puzzle, we want to constrain this rocker that we've already had on here. And we want to take the, what is it, the front plane there. Again, that's just, the names are immaterial. I'm going to select that front plane. I'm going to constrain that to the right plane of the assembly. Boop. Now I want to constrain. You can see there's actually, if we look back at the graphics in the slides, you can see we want it in this orientation and not this orientation. So I'm going to select mate. I'm going to select that hole, and I'm actually going to constrain that to this rear one back here. And hit OK. And now, SOLIDWORKS may misbehave, and if it does here, I'm going to tell you why and show you how to make sure it doesn't happen, but I'm going to press forward here. Select that hole, and select that hole. Okay, that misbehaved in sort of the way I expected it to. If you'll notice here, this is not quite what we wanted. Oh, that is actually what we wanted. So basically, like I said, so SOLIDWORKS there went to, like, it satisfied the mate while moving the part the least amount that it had to from its existing orientation, and that put it in that weird sort of crisscross state that it had it in there. And just as we were dragging around, it sort of jumped to the other state. If you do run into a situation where it's not really, say that didn't actually do what you wanted it to, you can sort of delete that constraint and then sort of reposition things. So if it was flipped the other way around, if it was flipped back here, you could reposition it here. That way you make sure that the closest sort of solution to the set of constraints that you're asking SOLIDWORKS to do is the one you want. All right, cool. I'm going to go ahead and hide some more of these planes just to declutter things. But yeah. So we now have, this is basically what we wanted here. We have you'll notice that there are still these characters, the parentheses, dash, close parentheses. So this is not fully constrained, but we want it to be. We don't want it to be fully constrained. We want it to be constrained in exactly the way we want it, and that's what we've done by applying the constraints in the way we have. Now, if you do have situation or systems like this that have a degree of freedom, but let me rephrase that. Obviously, if this was a real 4-bar linkage, obviously, the parts are going to collide, and physics won't let you do this. SOLIDWORKS, however, is not checking for, it's not applying collision detection, so it doesn't know that you don't want this. So what you can do sometimes to sort of better constrain your models to be closer to how they are constrained in reality is we can use some advanced constraints. So if we go up to mate, and I believe right here, so these are the standard mates that we've been using. But if I'm going to hit that drop down, and we can go down to advanced mates, and also mechanical mates, and so they're, you can make gears so they rotate together, cams, screws, various other advanced mates. But what we're looking for here is, I believe, limit angle. So what we can do here is say select just some reference, that face and that face, for example, and we can here define sort of a minimum and maximum value. So I'm going to define 10 degrees and 170 degrees. And we'll see how close is that to our actual to our. All right, so yeah, you can fine tune those values so it is closer to where some parts will actually bottom out, but that gives us some indication of how this is going to be constrained in reality. Cool. All right, I believe there is just one last thing that I want to show you guys with this exercise, and that is replacing components and then replacing assemblies. So what I'm actually going to do here. So these are all of our parts, and these are subassemblies, and then this is our master assembly. What I'm going to do is I'm going to take the coupler link here. So that is this part specifically. I'm going to make a copy of that. I'm going to paste. I'm going to rename. I'm going to call that coupler 2 link. And then I'm going to take our subassembly, and I'm also going to copy that. So I'm going to copy, paste, rename, and I'm going to call this coupler 2. So we've made a copy of coupler 1 called coupler 2, and we've made a copy of coupler 1 link called coupler 2 link. So I'm going to open up the coupler 2 assembly. So nothing has actually changed here. This is currently still the same as the old coupler. But to give us the option to change it, I'm actually going to select both of these links here. The coupler 1 link. I'm going to right click, go down to replace components, which I showed you in exercise 1. And I'm going to replace both of those instances with, I'm going to change the part, or change the filter here from assembly to part. I'm going to select coupler 2 link. And because coupler 1 link and coupler 2 link are the same geometry, they're just copies of one another, we don't have to reconnect any of these features. So I've hit OK. So what we've effectively done here is just replaced, we've replaced the link, both metaphorically and literally. We've replaced the link in SOLIDWORKS to a new copy of the link, the part. That's a bit confusing, I recognize. All right, so we now have this new subassembly. If we go back to the master assembly, I'm going to take one of these couplers, and I'm going to replace it with our new subassembly. And again, since nothing has actually changed yet, all of those links are fine. So now, these two instances are they're not two instances of the same subassembly, they're two separate subassemblies. So now I'm going to go back into coupler. I'm going to open up coupler 2 link, and then I'm actually going to change some of the geometry. So the way this is currently defined, or the way this is constructed, is we just have this single extrusion. If we edit it, oop, I see blue. That is bad. Oh, okay. Actually, the blue there doesn't matter. That's just placing the holes. Sorry. I'm going to change the center to center distance between the holes of this link. I'm going to change that to 100 millimeters from 75. I'm going to back out. And I'm going to, this by the way is the rollback bar. This is one of the really powerful things about engineering CAD that distinguishes it from other types of 3D modeling that aren't intended for engineering, is that, you know, this part file doesn't just store the information that describes the sort of final geometry. It stores all of the steps required to make it. So at any given time, you can sort of travel back in time by dragging this rollback bar up to see what the model was like with at a previous state. And then you can roll it back down, and that'll apply all the changes. Anyhow, I'm going to save. I'm going to go back up to coupler 2 assembly. And it'll say, you know, models contained within the assembly have changed. Would you like to rebuild the assembly? And that basically means is that's going to refresh all of the various links. And it just timed out there and did it automatically. And it did. We didn't actually see it change, but those links are now a different length. So we're going to go back up to the main assembly. Oop, there we go. You can see it hasn't rebuilt yet, so it hasn't updated the constraints. But if we hit yes, it will rebuild, and ba-bam. We now have a non-parallel 4-bar linkage as opposed to a parallel 4-bar linkage. So as opposed to previously, you know, this face would remain parallel with this face. If you have a non-parallel 4-bar linkage where these two links are different lengths, then it will no longer be parallel. And so you can tune these different lengths. Say we want to make this one shorter. So I'm going to edit that sketch. I'll make it 50 millimeters. I'm actually going to move those holes too. Make those 30 millimeters apart. Save, and then go back up. And then have it rebuild the assembly again. Ba-bam. And again, it's sort of bottoming out, given that we gave it that mechanical limitation with that advanced constraint. Where is that? Let me find that. I believe if you want to just see all mates within an existing assembly as opposed to one on a specific part, you can hit this drop-down menu here, and we can track down. All right, that limit angle one there. I'm just going to go ahead and suppress that. So that was that advanced mate that we used to make sure it didn't collide. And actually, so if this was something we actually cared about that we were actually designing, so we'd want to, based on this, we'd want to change some dimensions to move those holes so those parts were no longer colliding. But so this is sort of meant to illustrate something that's sort of common when you're actually doing CAD work for designing multiple parts in an assembly. And that's you'll sort of design a first draft of all of your individual parts. You'll assemble them. You'll see how they interact. You'll spot problems here, like two parts that collide. You can adjust the dimensions within individual parts and see how that affects, if it's something that moves, you can see how that affects its motion by dragging around here. You can see how those angles change. This is very, very commonly used, and it's a very powerful technique for designing mechanical systems. And with that, I think we are done with this exercise. So I'm going to hit save for everything and go ahead and close out of all these files. Clear up our workspace again. Excuse me. All right, I'm going to take another like 30 seconds to a minute and give you guys time. If you have any questions you want to ask, then again in Discord, let us know. All right, if not, I think we'll go ahead and move on to the final exercise. All right, so we have a valve here. So this is like a cam and rocker and valve from an internal combustion engine, from a gas or diesel engine. And obviously this is you can't have parts like this interacting in a specific way without some sort of housing to constrain everything. But for our purposes, we're just going to use this as an example to show some of those more advanced mates, specifically the cam constraint. Oop, we're going to show you how to do. So if you go back to your exercise 4 folder, and if you downloaded the zip file via the link we gave you, we actually forgot, we omitted one file. So if you follow that link again, I believe that takes you to Google Drive. There's a separate file called a.exercise4 that is separate from the zip file. If you also want to download that to have here. Cool. So I'm going to try to remember. Okay. So let's go to SOLIDWORKS. Let's open up. I believe. Yeah. Okay. So this assembly, I've gone ahead and prepared with a few datums in a few specific locations. Just going to make some of these planes visible so we have a bit of a frame of reference as we're orbiting here. Without actual physical solid geometry, it can get a little confusing as to what the hell you're looking at as the orbit. All right. So I'm going to go ahead and insert some components here. I'm going to navigate to our exercise 4 folder. So there are three components. There's the cam, the rocker, and the valve. And you can go ahead and when you're inserting, you can insert multiple parts at the same time, and it doesn't matter too much. And it'll prompt you one at a time to sort of place these. Location is kind of arbitrary. All right. So what I'm going to do, I'm going to start out with this valve here. And if I recall, when I made this, there's actually an axis there. All right. So we're going to start out with this valve. So what we're going to do is we're going to constrain this axis to this axis we've prepared in our assembly. So that valve can now move up and down. It can still rotate, but since it's an axisymmetric part, we don't really care. Believe, yeah, I'm just going to leave that like that. This cam here, since that was the first one we inserted, again, SOLIDWORKS applied that automatic fix constraint to get rid of that. I'm going to right click and hit float. And I believe you can constrain a cylindrical face to an axis in SOLIDWORKS. I found it frustrating at an internship that PTC Creo actually does not let you do that. You have to constrain axes to axes or cylindrical faces to cylindrical faces, and you can't cross between them, which is dumb and frustrating. But anyhow, so you can either select that cylindrical face, or if I hit escape, you could select the actual axis, this datum axis that's defined within that cam part. You can also constrain that. And hit OK. Doesn't matter which. Now to just lock things in position, I'm going to go ahead and take the front plane there, just sort of the mid plane of that cam, and I'm going to go ahead and constrain that to what in the assembly we have called the right plane. That is just to lock it. So the only degree of freedom this now has is the one we want, which is rotational. So now we just have to constrain the rocker part, and you can see that's asymmetric. So I'm going to reference the view here. So it looks like we want the long side, and it's subtly, it's not particularly obvious. We want the long side over the cam. So what I'm going to do here is I'm going to take the rocker, I'm going to grab its front plane, I'm going to constrain that to the right plane here. Oop, it jumped there. All right, we actually want it the other way. So I'm going to hit flip mate alignment. So it'll have the SOLIDWORKS chooses weird axes to flip parts around when you do that, but just going to leave it like that. Cool. Now I'm going to navigate here to the rocker. I do not have an axis defined there. So I'm going to go ahead and select the cylindrical face, and I'm going to select rocker axis. And call that good. By the way, I may not have ever made it clear. You can rename any datum you want. So it's like you'll see these axes at some point. I renamed them. They showed up as like axis 2 or axis 3 or whatever SOLIDWORKS' default name is, and you can rename those. So here, for example, I could call right plane. If I want to clarify, I can right click. Oh, you can't actually. You have to do that weird like click and then click again, but a second later. It's a little strange. There's no just straight rename option. But I'm going to call that just, I don't know, valve midplane. And then you can see that that updates the name here. That can help. Naming features definitely helps when you've got a lot of them in a given part or assembly. It can help keep things straight. I'm going to go ahead and hide those other planes though. All right, cool. So now, we got our valve, moves up and down, rocker moves like that, cam moves like that. But we want these to move together. So what we're going to do here, and again, so this is omitting parts. So this is omitting the housing. In reality, this valve would be spring loaded. But this is just to illustrate some of the constraints you can apply. So you're going to go to mate. I'm going to select this sort of top hemispherical surface on the valve. I'm going to select the bottom face of that rocker, and it'll default to the one we happen to want here as the tangent constraint. So hit OK. Back out of mate there. So now, as this rocks, you can see the valve there moves up and down. And now the slightly trickier one here is the cam to rocker. So if we were to just use sort of the standard mates here, which is what it's sort of default selecting from, if I were to select that surface and just go with SOLIDWORKS assumes you want those to be tangent. If I just went with that, you'll actually notice this is not behaving the way we'd want it to behave. What it's actually doing here is it's almost like so it's like it's treating this face as a complete cylinder and making sure that this face is always, sorry, it's treating this face as like a complete cylinder and then making sure this face is always tangent to that sort of imaginary cylinder. So you can see there, that is, SOLIDWORKS is doing exactly what we asked it to do. And that's because what we asked it to do is not actually what we want it to do. So instead, we don't want a tangent constraint. There is a specific cam constraint. So I'm going to navigate, select the cam there to that tangent constraint which is applied. I'm going to go ahead and delete that. So now instead, I'll go to mate. Instead of standard mates, we're going to go down here to mechanical mates and select the cam option. So what this is now asking us to do is select the cam path. So if I select one face here, it'll actually automatically select the adjacent tangent faces. It looks like I might have missed one, so I'm going to hold control and go ahead and select that other face just to make sure. All right, cool. So it's got all of those faces selected. And that SOLIDWORKS just automatically popped me over to the next option, cam follower. And that is this face that we want to select. Cool. And we do that, we can hit OK. One or more of the cam entities has a radius less than that of the follower. This may result in errors when dragging the components. Cool. I think that's just SOLIDWORKS giving a warning. I don't think that'll be an issue. We're just going to go ahead and hit OK. All right. Now we're going to back out of the mate tool. So this should be constrained in the way we want it to. Cool. So this is actually behaving similar to how we'd want it to behave in reality. If you're interested at all in cam design, that is actually, they may have changed it, but ME352, which I believe is now ME354, Machine Design 1. When I took it, Machine Design 1 covered cam design in a decent amount of detail. They may have moved that to Machine Design 2, though. Anyhow, let's I guess I shouldn't assume I'm talking to mechanical engineers. If you're a mechanical engineer and you're interested in this, will likely be covered in one of your classes. But anyhow, so it's like actual cam design is a bit more complicated than just draw two circles and bridge it with some tangent lines. You want to make sure not only that it's following the position that you want, but it's getting the actual linear velocity here is what you want, and the acceleration and the jerk, and so you look at all those different derivatives and make sure it's all continuous in the way you want it to be. But yeah, we're not designing an engine here. This is just to illustrate that there are more advanced mates that give you options for visualizing how more complicated mechanical systems might work. And with that, I believe we have concluded the exercises we had planned here, a little bit ahead of schedule. So what I'm going to do here is I'm going to go ahead and stop the stream to YouTube, and then Angelo and I are going to hang out in the Discord for a little bit longer, and if you guys have any questions, we can talk about it there. All right, I think with that, I'm going to go ahead and